This is AP Calculus AB B, Unit 5, Lesson 2, Applications of Accumulation and Net Change. In this video, I thought I would take another look at Hooke's Law and do a problem involving that, but maybe with a little bit of a different look than was given in the lesson itself. So this is meant to be supplemental, so do make sure you go through the lesson materials, of course, as well. Okay, so we're talking about a mass on a spring. That's a fairly common physics problem, right? You've got a spring and a mass on it. It has an equilibrium point, right, that we might consider the 0 point. And then it takes force to displace the mass, either up or down. Okay. Let's say in this case we're going to pull it down. Within small increments, small changes, that for the force up and down is basically the same. Okay. So we're displacing it with a force. According to Hooke's law, the amount of force is directly proportional to the displacement. Okay. Now they used d for displacement. I prefer not to use d because we already used d in the general integral, and I'd rather do dx than dd. All right. So I'm going to use x. So proportional to the displacement. So k x, where x is the displacement from the neutral position of the spring. Okay, so let's say that the force needed to displace this 2 meters from, 2 meters from its initial position is 6 newtons. Okay, in that case then, F of 2 equals K times 2 equals 6, and we get that K equals 2. So we can specify a specific solution or a specific function, F of X equals 2. No, I'm sorry, 6 divided by 2 is 3. 6 divided by 2 is 3. Okay, so f of x is 2k, or 2x. F of x is 2x. Okay, and so if I want to displace the spring 4 meters, then there I go with 2 again, with 3x. If I want to displace it 4 meters, 4 times 3 is 12 newtons, right? So F of 4 is 12 newtons, okay, of force. Now work in physics, work is measured as force times distance, or force times displacement. So force times distance, or x. Okay. Work is force times displacement. And what we want to do is answer this question: how much work is done displacing the mass? Let's do 8 meters from neutral. Okay. Now if we could just calculate the force for 8 meters, which would be 8 times 3, or 24 newtons, we could say, well, 24 newtons times 8 meters. But that would be assuming that we apply the same force the whole time. Okay. So let's kind of make a chart here of displacement. Here's 0, and here is 2, 4, 6, 8. 8 meters. Okay. This is our x-axis here, and we're displacing 8 meters. Let's look at just a little thin slice. Little thin slice here. Okay, where the width is delta x. The work done in that little slice is the amount of force done at the x value, of force dependent on x, whatever that x value is. Let's call this x1. So force at x1 times the little slice, delta x. Now imagine, if you will, taking an infinite number of these slices and calculating the work done over each of the intervals. And what do we call that when we take a sum, an infinite sum of slices that get progressively smaller and smaller? Well, that's a Riemann sum. That is an integral, right? So work is force delta x, or work is, over the entire range, the integral from 0 to 8 of force of x dx. Dx replacing delta x. Delta x is a small difference. Dx is what we call the integral differential. Right? So hopefully that makes sense, that the work is the integral of force over distance. Okay? And so let's solve the problem. The work done over the displacing it 8 meters is the integral from 0 to 8 of, in this case, 3x dx, which is 3x squared over 2, or 3 halves x squared, from 0 to 8, which is 8 squared, 3 halves, 8 squared. 8 squared is 64 divided by 2 is 32 times 3. Actually, let's do 0 minus 0. So, 32 times 3 is 96. 96 Newton meters. A Newton, by the way, is a kilogram meter per second squared, which is kind of fun. All right. But anyway, Newton meters, 96. So that's the amount of work done in displacing. Hopefully that makes sense. Just a little bit of a different look at it than in the lesson.